Okay, so this is chapter 15, the chemical equilibrium. So first question is to write the correct equilibrium constant expression for this chemical reaction. So in this chemical reaction, we have 2 SO2 gas plus 1 O2 gas in equilibrium with 2 SO3 gas. When write expression for the equilibrium constant following the following guidelines. 1. Only include products or reactants in the gaseous or aqueous state. Do not include those products or reactants in the liquid or solid state. Secondly, always write products on the top of the expression, so the expression may be really a fraction. So therefore, sometimes maybe not a fraction, just a number. But anyhow, just write on the top of the fraction for the products, and then for the reactant, write at the bottom of the fraction. Thirdly, the coefficient in the balanced equation, balanced chemical reaction equation becomes exponent. Okay, so for this example, we have our products SO3 gas and 2 reactants O2 gas and SO2 gas. So they are all gas. So therefore, they should be in the expression for the K. And all the choice is Kc. Sometimes we might write Kp, but in this example, we'll write Kc. So Kc will equals. So usually it will be a fraction. So a fraction has the top and the bottom. So products on the top, and our product will be the SO3. When we write Kc, so C means concentration. So C is for concentration. And the concentration unit is molarity. Okay. So as we learned in chapter 14, the molarity can be represented by the angle bracket. Okay. So therefore, the molarity of SO3, it will be the angle bracket SO3. Okay. And then this is the products and the molarities. Then see the last guiding line, the coefficient in the balance equation becomes the exponent. So we can see the coefficient for SO3 in this example is 2. So therefore we'll use 2 as the exponent. So we'll put 2 here. Okay. And then we'll check for those reactants, only include those gas or aqueous for the reactant and also the product. But the reactant should be at the bottom. So we have one reactant is SO2. Okay. Again, we use angle bracket represent molarity. SO2 has the coefficient 2, so therefore raised to the second power. And then we have that O2. And then O2 also use molarity. We use angle bracket. And O2 has coefficient 1, so therefore to the first power. Okay, and then this will be the correct equilibrium constant expression or equation or formula. Okay. So second question, similar. You want to write the equilibrium constant expression for this reaction. So for this reaction, we have ammonia NH3 aqueous plus H2O liquid in equilibrium with ammonium ion NH4 plus aqueous, the hydroxide ion OH1 negative aqueous. Similar guiding line. So we'll write Kc or Kp or those or Kc, so we'll write Kc equals some fraction, products on the top. So we write Kc as a fraction, products on the top. In this example, the product is ammonium ion NH4 plus, and then we use angle bracket again to represent molarity. We use coefficient as exponent, So in this problem, all the coefficients for these two products and for those rectangles, they are all 1. So therefore, just to the first power. To the first power, you don't have to write 1 as exponent. The second product is hydroxide OH1 negative, and then similar. And then the reactant, we have 2 reactants. One reactant is ammonia NH3, so that is in aqueous state, so we put here. And then that H2O liquid we will not put here. So therefore, this is the final answer. And then you can see the answer should be matching D. And by the way, the answer for the first question, it is matching the A. Okay, so question number 3 is for this Haber process, N2 gas plus 3H2 gas produce 2 ammonia gas, and we are given this Kc equals 9.60 at 200 degrees Celsius. We want to find out Kp for this reaction at this temperature. So what do? We'll use this equation, Kp equals Kc times RT to the delta N power. And in this equation, R is the gas law constant, and we'll use this number for R. R equals 0.08206, the unit ATMs times L. L is the liter, and divided by mole times Kelvin. And T is the temperature in Kelvin. Delta N is the sum of gaseous products coefficient minus the sum of the gaseous reactant coefficient. So for our problem, all those substances, these products, this reactant, they are all in gaseous. So you need to find out the delta N by take their coefficient. Okay, so see what are the sum of the gaseous product coefficient. There's only one gaseous product, which is NH3. The coefficient for this is 2. Therefore, this is the sum. Okay? There's only one product, 2, so 2 plus 0. And then we will subtract by the sum of the coefficient of all those gaseous reactants. The sum of gaseous reactant coefficient. So we have one gaseous reactant, which is N2 gas, coefficient is 1. Okay? And then plus the other reactant is also gaseous, which is H2. H2 has a coefficient of 3, so therefore 1 plus 3. And then you get 2 minus 4, you get negative 2. Okay? And T should be in Kelvin, so the given temperature, small t, is 200 degrees Celsius. Then we can do a conversion. We take 200 plus 273 equals 473 Kelvin. Okay? Now we have all the numbers we need. We will just plug those numbers into that equation and calculate this Kp. So we say Kp equals Kc, we have the number 9.60, has no unit, then times in the bracket R 0.08206, and as it has this number, and then we have that temperature, so therefore times, so this multiply the temperature will be 473, and then we will raise to the power negative 2. Alright, so therefore you just take those numbers, do the calculation. Let's see, we will keep it right 9.60 for this one. Then we take these two numbers, multiply. We get I run into this 4 sig fix, and then to the negative 2 power, and it ending as 9.60 times So this together to the negative 2 power become 0.000664. Then finally you multiply these two numbers, you get 0.006374. We will use scientific notation, write as 6.37, keep 3 sig fixed times 10 to the negative 3. So therefore this answer is B. Next question, number 4. Question number 4 is given the equilibrium constants for the following two reactions in aqueous solution at 25 degrees Celsius. So one equation is HNO2 aqueous produce H plus aqueous plus NO2, one negative called nitride, has Kc this. Let's number those equations. We'll call this equation 1. Okay. The second equation is sulfurous acid H2SO3 aqueous produce 2H plus aqueous plus sulfite ion. This will be 2 negative. Okay. And Kc is this. So let's call this equation number 2. Then want you to find out the value for Kc for this equation. So let's call this equation number 3. Okay. So then we need to do some manipulation of equation 1 and 2. Okay. So what we do, we will examine what appears in the equation 3. We want to find out the Kc for. So in this equation 3, we have 2 HNO2 on the left. We have 2 NO2 and negative on the right in this equation 3. And both of these two guys, they only appears in equation 1. In the right location. In equation 1, we have this HNO2 on the left, NO2 and negative on the right. So they appears in the right location, but the number not right. So we need 2 and 2. In equation 1, we have 1 and 1. So we need to multiply equation 1 by 2. Then this is the rule. So when you multiply, or if you multiply an equation by 2 or by 3, by whatever you use to multiply, so if you multiply equation by 2, then the K for the new equation will be the K for the old equation raised to the power of 2. Okay? So now let's do that. So we will take this equation 1 multiply by 2. So that means you will have 2HNO2 aqueous, and then in equilibrium with 2H plus aqueous plus 2NO2 one negative aqueous. Okay, so this is the way we multiply equation by 2. Okay, multiply equation by 2. So when you multiply equation by 2, you multiply all the coefficients. So coefficient 1 becomes 2, coefficient 1 becomes 2, coefficient 1 becomes 2. So you still keep the reactant as a reactant, product as a product. You just multiply the coefficient. So then this, what I highlighted here, if you multiply the equation by 2, then this guy has a K, then this new K will equals the old K raised to the power of 2. So this old K is 3.5 times 10 to the negative 4. Okay? And so therefore, you will take this together and square that, or raise to the power of 2. Okay. And then let's examine what we need to do for equation 2. So in this equation 3, we need this sulfide ion on the left, and we need this sulfuric acid on the right, and these two only appears in equation 2. So equation 2 has SO3 2 negative and has this H2SO3, but they are at the opposite position. So in equation 2, we have SO3 2 negative on the right side of the arrow, but we need SO3 2 negative on the left side of the arrow in equation 3. So we need those in equation 3, but both are there, so we need to reverse equation 2. Okay, so if you reverse equation 2, so here's the rule. If you reverse any equation and get a new equation, then the key for the reverse equation will be the reciprocal of the old equation. Okay, so let's use this example to see what this really means. Let's first reverse this equation 2, which means you will write those products in that equation 2 as reactant in the reversed equation of equation 2. So these two in equation 2 was the products. Now I write them as reactant. And then that reactant in that equation 2 become the products of the reversed equation 2. So that's what we mean by reverse equation. And then what do we mean by the K for this reverse equation? So let's say this will be the new K. Okay? So the new K for this reverse equation, let's see, so that new K, maybe they call the new K1. Okay? And this called the new K2. But this reversed equation 2 called the new K2. So this reciprocal, which means 1 divided by that K old K. So the old K for the equation 2 is 1.1 times 10 to the negative 9. Okay? Now all together, so this will be the new K2 for this reversed equation 2. And that is the new K for the new K1 for the new equation 1 by multiply the old equation by 2. Now, another manipulation is adding two equations. So now we have this new equation 1 and new equation 2. If we adding these two new equations, and if we can show by adding these two new equation 1 and new equation 2, and we get equation 3, then there will be another rule, and we will see the other rule is the K for this equation 3 will be the by multiply the K of those equations you use in the adding. Okay, now let's see this example. We first want to check this new equation 1 and this new equation 2. We're adding them together to get equation 3. Okay? So when you add equation, when adding chemical reaction equations, we add all the reactant and add all the products. Okay, so we will see what are the reactants in the new equation 1, in the new equation 2. In the new equation 1, we have one reactant, which is 2HNO2 aqueous. Then we will add to those reactants in the new equation 2. So that will have two reactants. One is H plus, the other one is sulfide. So that's how we adding the reactants with reactant. Then we'll add the products to the products. So we have two products in reaction in new reaction 1. So we have 2H plus aqueous plus 2NO2 1 negative aqueous. So those are the two products we get from new equation 1. Then plus there's only one product in new equation 2. So that is H2SO3 aqueous. So that's the preliminary result after we adding those. And then you can see there are something common on the left side and also on the right side. So what is common is this 2H plus, 2H plus. So we cross these two out. And then we get the net. So we will get 2HNO2 aqueous plus SO3, 2 negative aqueous, because that's already cancelled out, in equilibrium with 2NO2, 1 negative aqueous plus H2SO3 aqueous. So this equation is from adding new equation 1 with new equation 2. Okay? So this equation here, let me highlight, is we get that one from adding the new equation 1 and with new equation 2. And then we compare this one with the given equation 3. Then we see they are the same. So therefore, this equation I highlighted here, getting by adding new equation 1, new equation 2. Then this one will have the new K3, which is the K3 you want to find out. So therefore, K3 will equals that new K1 times new K2. Okay? And then we find out in new K1 is 3.5 times 10 to the negative 4 squared. And then new K2 is 1.1 times 10 to the negative 9. 1 over 1.1 times 10 to the negative 9. So therefore, you just do this calculation and okay, so what do you find out? Just take this number squared and divide by this number, and you get 1. Okay. So to keep the right number of sig fig, so you write, instead of writing 111, because this has, let's say, 3 sig fig. Okay. But this guy has only 2 sig fig. So therefore, if you keep 3 sig fig, that's not right. You want to write in scientific notation, you just write 1.1 times 10 to the positive 2. So like that. So in that way, this guy give you 2 sig fig, and this exponent doesn't matter. So therefore, the answer will be E. Okay, next question, number 5. You want to find out, let's see, for this given problem, you want to find out the equilibrium constant Kp. Okay, so equilibrium constant Kp or Kc you can get by, like what we did before, is give you some equation, we know the K. You can also get by write up the expression for Kp, then substitute those partial pressure at equilibrium, or those concentration at equilibrium. And this is the problem, because this gives you all those partial pressure for all these 3 substances that in gaseous state at equilibrium. So you see, just identify this equation. There are 2 SO2 gas, O2 gas, and 2 SO3 gas. So you write up this just question mark. So just write the K or Kp, Kc. So Kp as what we did in the first 2 problems. So the urea fraction, the product on the top. So in this example, I'm going to use partial pressure. So the product is SO3, and then use coefficient as power. So this coefficient is 2, and then we have 2 reactants. So we're all going to use partial pressure. So SO2 coefficient 2. Then we have the partial pressure for O2 coefficient 1. So then this is the equation of the formula for Kp. So secondly, we'll make a list to make sure you don't substitute it wrong. We'll make a list of the given partial pressure at equilibrium, and let's say starting from the first number. So first number 0.669, which is SO2. Okay? So we list PSO2 equals 0.669 ATM. Okay? So make sure even though Kp or Kc don't have a unit, but when you calculate Kp, you use ATM. So when calculate Kp, use ATM at equilibrium. Okay, so we have the partial pressure of SO2 at equilibrium 0.669. And then we have the partial pressure, the next number 0.495 is O2. So O2, PO2 is 0.495 ATM. Then the last one, PSO3, equals 1.0851 ATM. So once we have the list, we just plug in those numbers into the equation for Kp. So therefore, Kp will equals the partial pressure for SO3 is 1.0851, and we raise to the second power. And then we have 0.669 for SO2 raised to the second power, then 0.495 for O2. Right, so you square the total number, you get 1.177, and you square and multiply those two numbers in the denominator, we get 0.2215. So adding up with 5.31 and 5.31, the answer will be B. Right, next question 6. So we have this closed system initially contained this much more of H2, this much more of I2 at this temperature is allowed to reach equilibrium, and analysis of the equilibrium mixture shows that we have a concentration of HI. Then we want to calculate the Kc. So for those kind of problem, we are not given all the concentration at equilibrium. We only have one concentration at equilibrium for this guy, and then those two concentration is the initially. So therefore, we had to use IC table to find out all the equilibrium concentrations. And to do that, you just use the equation as a guiding line. So our equation is H2 gas plus I2 gas in equilibrium with 2HI gas, and then we make an IC table. So I means initial, C means change, E means equilibrium. So we want to summarize our data in the table, and then we want to find out all those at equilibrium. Okay, so this very important ICE table. Alright, so let's summarize. The initial concentration for the H2 is 1.000 times 10 to the negative 3. Then I2 is 2.000 times 10 to the negative 3. So this did not tell you the initial, so by imply is 0. And then tell us at equilibrium we have this guy concentration 1.07 times 10 to the negative 3. Okay, so at equilibrium we have HI concentration. Okay, now the purpose of this IC table is using this information to find out those two numbers here. Then we can plug those two numbers into the expression for K to find out K. So therefore we have to do the process. So we first use this